Here we've got a reversible power cycle. It's going to receive energy QH, which is shown right here, by heat transfer from a hot reservoir, which is going to be at a temperature TH. And it's going to reject energy QC by heat transfer to a cold reservoir, which is going to have a temperature TC. Now we've got four different things we're going to do here. The first one, we're going to let TH be 1600 kelvins, so that would be the temperature up here. The cold reservoir is going to be at a temperature of 400 kelvins. It wants to know what the thermal efficiency is. Notice this says it's a reversible power cycle. Remember, reversible is kind of the ideal case that you would have. So let's start on part A, and then we'll go through the other three parts after that. So TH is going to be 1600 kelvins. TC is 400 kelvins. We want thermal efficiency. Remember, thermal efficiency is that eta symbol. The equation we're going to use, since this is reversible, will be 1 minus Tc over Th. So really easy calculation. We just do 1 minus 400 Kelvin over 1600 Kelvin. Notice the units cancel out. And we get 0.75. You could also write that as 75%. So this would be your thermal efficiency. So it's got an efficiency of 75%. That's part A. Now part B, we're going to let TH be 500. TC is going to be 20. This time we're given work for the cycle. It's 100 kilojoules. We want to know QH and QC. Both of those need to be in kilojoules. For this one, let's go ahead and write these values out. All right, so that's what we've got. We need QH and QC. Now remember that your eta is the work of the cycle per QH. So this equation works for any kind of power cycle, whether it's reversible or not. That means that we could say work of the cycle over QH is equal to 1 minus Tc over Th. With this, now we can find QH because we know all these other data points. So let's plug in the numbers. So QH, once you solve this equation for QH, you're going to get work of the cycle over 1 minus Tc over Th. That'll give you 1000 kilojoules per 1 minus 293 kelvins. Notice we have to convert over from Celsius to kelvins, and it's going to be over 773 kelvins. Kelvins will cancel. That's going to give you 1610 kilojoules. So this is QH right there. So that's basically your heat transfer from that hot reservoir to that system there. Now we also know we need to find QC now. We need another equation. We know for any power cycle that the work for the cycle is going to be QH minus QC. Now if we take this equation, solve for QC, you're going to get QH minus the work of the cycle. So that gives us QC equals 1610 kilojoules minus 1000 kilojoules, giving us a QC value of 610 kilojoules. So that'll be the heat energy that's discharged to that cold reservoir. All right, so both of these are for part B. Now part C, we've got the efficiency given at 60%. We're also given TC, and what we want to do is find TH. We want TH to be in Fahrenheit. Now with this one, again, since it's reversible, we can use the fact that eta equals 1 minus Tc over Th. We're given eta, we're given Tc. Only unknown here would be Th then. So we're going to have 0.6 equals 1 minus. Don't forget to convert over to Rankine. So we'll have 500 Rankine over TH. Then you can solve for TH. You'll get 1,250 degrees Rankine. We want it in Fahrenheit. That's 790 degrees Fahrenheit. That is the temperature then of the hot reservoir if we have these two conditions here. Okay. And lastly, we have part D. Part D, we're given eta. Now it's 40%. And we're given TH. It's 727 degrees Celsius. We want to find TC in degrees Celsius. So again, same equation we had before. So eta is going to be 1 minus TC over TH. We just need to plug in our values. So 0.4 equals 1 minus TC over, convert this over, and I almost forgot. So that'll be 1,000 Kelvin. Now you can solve for TC. So you get 600 Kelvin, which that's 327 degrees Celsius. That would be the temperature of the cold reservoir. Pretty simple calculations here. This one, the main thing you had to pay attention to is that it said it was a reversible power cycle. So because of that, you could use this equation right here. All right. Have a good one.